Hello, welcome to this learning module. In this learning module, we are going to go over the electromagnetic spectrum, the light spectrum, the frequencies of the various frequencies and ranges of light. Now, you may have had a lecture on the electromagnetic spectrum in a different course in the past. Maybe it made a lot of sense. Maybe it was really confusing. Doesn't really matter. We're going to go over it again here, and I can't let you leave this course without really finally grasping the electromagnetic spectrum. So I'm going to give you some tips and tricks to help you understand and grasp the electromagnetic spectrum. Electromagnetic spectrum is the light spectrum. It's broken into various ranges. We're only able to see a very small portion of this range, but there are other ranges of the electromagnetic spectrum. So the first thing we're going to do is just kind of go through this list and orient you to these ranges. So over on the left side, we have gamma rays. These are things that are from radioactivity, radioactive decay. X-rays, just like medical X-rays. Ultraviolet light, this is what gives you sunburns and ultimately skin cancer. Visible light, that's what we see, and is broken down into the violet through the red. Infrared light is like heat lamps, like at cheap fast food restaurants. Microwaves are what we use at our microwave ovens. Interestingly, also, cell phones operate in this frequency band. And then finally, radio waves, just like we listen to in our car. The radio wave spectrum is at the right end of the spectrum. All right, so there's two values, two variables that we need to be comfortable with the electromagnetic spectrum. I'm not going to make you memorize a whole lot of numbers here, but in a relative sense, you need to be aware of the trends in the electromagnetic spectrum. And the two variables, the two values that you need to be comfortable with are wavelength, and wavelength we denote with the Greek letter lambda, and energy. Now, energy is proportional to frequency, so we'll often talk about frequency, and frequency is denoted by the Greek letter nu. That's not a lowercase v, it's the lowercase Greek letter nu. So frequency and wavelength are the two values that you need to be familiar with. So when you look at this list, let's see if we can kind of get some generalities going. When you look at this list, one side of this list looks a little bit more dangerous than the other side of this list. The gamma rays, the radioactivity, the X-rays, the sunburn, the ultraviolet rays, the skin cancer, that's a little bit more dangerous than radio waves and microwaves. And so if something is more dangerous, then it stands to reason that it is higher energy. Things that are higher energy are often more dangerous than things that are lower energy. So that's the first thing to keep in mind. When you just generally look at this list, just remember that the more dangerous side is higher in energy. So the radioactivity, the X-rays, the gamma rays, the ultraviolet rays, the sunburn, skin cancer, those are more dangerous, so therefore they're higher in energy. Which means then that the radio waves, the microwave side, is lower in energy, less dangerous. All right, so what does that have to do with frequency and energy, frequency and wavelength? So we just kind of talked about energy. So the more dangerous side is higher energy, the less dangerous side is lower energy. The more dangerous side, higher energy, has a lower wavelength, and that's, I think, is sometimes where we get confused. Shorter wavelength. I think that's sometimes where we get confused because the trends are pointing in opposite directions. So when we have a lower energy, we have a longer wavelength. Energy is proportional to frequency, so where we have higher energy, we have a shorter frequency. That's not true. Where we have a higher energy, we have a higher frequency. And where we have lower energy, we have lower frequency. All right, so I even as I'm saying this out loud, I can hear myself confusing myself. So let me give you my best tip for remembering the trends that you need to remember. Long wavelengths are very low energy, and short wavelengths are very high energy. So if you have a range of light, a frequency of light that's very low energy, very long wavelength, it has a very low frequency. And if you have a higher frequency, shorter wavelength, then it is higher in energy. So that's how you can remember it. Long wavelengths are low energy, short wavelengths are high energy. Low frequency is longer wavelength is lower energy. Higher frequency is shorter wavelength and higher energy. So you got to be really comfortable with that relationship. And then from there, you have to be comfortable with the things that are on the left side of this particular diagram are the things that are higher in energy, higher frequency, shorter wavelength. The things that are on the right side are the things that are lower in energy, lower frequency, longer wavelength. And that is true for the visible spectrum as well. The visible spectrum is broken up into the violet through the red. And so these are the two numbers that I'm going to need you to know from this diagram. The violet end is around 400 nanometers. The red end is around 700, 750 nanometers or so. So then, which side of the visible region is higher energy? It's not entirely clear because visible energy is all about there's nothing really more dangerous about any visible light. But if you, again, keep in mind that the things on the left side of this diagram are the more dangerous higher energy, then the same would be true for the visible region. The left side of the visible region would be the higher energy. So the purple side is the higher energy side. And if it's higher energy, that means it has a lower wavelength, a shorter wavelength, and a shorter wavelength and a higher frequency. And the red side then is the side that's lower in energy. And if it's lower in energy, that means it has a longer wavelength. And if it's longer in wavelength, that means it has a higher wavelength and a lower frequency. So the red side is lower energy, the purple side is higher energy, the red side is longer wavelength, the purple side is lower wavelength. So the purple side is higher energy then. What's a little bit past the purple side? A little bit past the purple would be ultraviolet. It's ultra, the violet. And the ultraviolet then is even higher energy, even lower wavelength. And the past the red would be the infrared. It's a little bit infra the red. It's past the red. It's the next region down. And if the red side is the low energy side, then infrared light is a little bit lower energy than visible, and a little bit longer wavelength than the visible. There's one last thing that you have to know about this spectrum. There is a bright red line in the spectrum, and it's about here or so. You must know this line in the electromagnetic spectrum. This line is the cutoff between ionizing radiation and non-ionizing radiation. So all electromagnetic wavelengths, all photons, are radiation. And radiation has a negative connotation, but it really doesn't need to. It's just a noun. It's just a way of describing the photons in the electromagnetic spectrum. What's important is the adjective in front of the noun. So to the left of this bright red line, this is ionizing radiation. And to the right of this line is non-ionizing radiation. You must know this line, very important line for the rest of your life. The line between ionizing and non-ionizing radiation is in the middle of the ultraviolet region. Why is that important? Ionizing radiation, again, remember, the left side of this diagram is the higher energy, more dangerous side. The shorter wavelength, the higher frequency side. So ionizing radiation is, yes, has enough energy to break bonds. Has enough energy to break chemical bonds. And that's really important because when the ionizing radiation breaks a bond, then that can cause damage. And if those bonds happen to be in something like your DNA, then they can cause damage to your DNA. And when you have damage to your DNA, one of the possible side effects of damaging your DNA is cancer. Now, our body's actually pretty good. We get bombarded with ionizing radiation every day. There's something called the background ionizing radiation. It's just the level of ionizing radiation we're exposed to every single day just being alive on Earth. It's unavoidable. And our body actually has pretty good repair mechanisms for repairing broken bonds. But if you get enough ionizing radiation or ionizing radiation in just the wrong place, then it can break a bond in, say, your DNA, and it can potentially cause cancer. Not every time, but can potentially. So the opposite is true for non-ionizing radiation. Non-ionizing radiation does not have enough energy. It is low energy. It does not have enough energy to break bonds, and therefore it cannot cause cancer. And the reason I bring that up is right here. So remember I said earlier that cell phones are in the microwave, operate in the microwave region, and cell phones are in the non-ionizing radiation side of this spectrum. The cell phones do not emit ionizing radiation. They emit microwave energy radiation. Because they cannot emit ionizing radiation, cell phones do not emit enough energy to break bonds, and cell phones cannot cause cancer. I know that's a common thing that you hear about sometimes, and it's just not true. Cell phones cannot cause cancer because they do not have ionizing radiation. They do not emit ionizing radiation. I mean, think about it. If they did, we'd all have leg cancer, right? Because we keep our phones in our pockets all the time. So as a now scientifically literate person who's been through organic chemistry, this is something that you must know for just walking around in the world. This is something you have to know. So this is what you have to know about the electromagnetic spectrum. You need to know the general trends of wavelength and frequency, and which wavelengths are higher or lower in energy.